Hey there, my name is Dylan, and I'm helping my good friend Duncan out to record this lecture series for your benefit. And today we're going to be studying Newton's method, a method for finding the roots of a nonlinear function, just like the bisection method that you studied last week, but this time we're going to approach it from a bit of a different angle, a little bit faster and maybe more useful in certain scenarios. So let's say I have an arbitrary function f of x, and it looks something like this. And so the root is right here, but we don't necessarily know that, and the computer doesn't know that. How we're going to go about this is we're going to start by picking an initial value. We'll call that x0. And so what we're going to do is we're going to take the linear approximation of our function at x0, and we're going to find the root of that function. So we're going to take the tangent line, and we're going to solve for this root, because that's something that we can do. It's nonlinear. You can do it. The computer can do it. It's a very simple problem. And so how we do that is this line, the equation for this line, will just be the first two terms in the Taylor expansion of this function. And we're assuming it's continuous and differentiable. So that's going to be equal to the value of the function at x0 plus the derivative of the function at x0 times your displacement from x0. And now what we want to do is we want to solve for the root of that. So we're going to set that equal to 0. So you're going to have 0 equal to f of x0 plus f prime of x0 times, we're going to call our new value, this root, we're going to call that x1, and you'll see why in just a second. So this is our equation for x1, and just rearranging things with a little algebra to solve for x1, we get that x1 is equal to x0 minus the value of the function at x0 divided by the derivative of the function at x0. And I'm sure you can all do that for yourselves to check. So this is our new point. We're going to call that x1. And the reason for that is this is going to be an iterative process, trying to get our x value to approach the root of the function. And we can't get arbitrarily accurate with this because that would take an infinite amount of time. So we're going to set some sort of tolerance value that's arbitrarily close to 0, whatever our problem calls for. So we'll just say that's approximately equal to 0, but just a little bit greater than, like maybe 1/100th, 1/1000th. And so now we're going to do the same thing over again. We have a new starting point, x1. We find the function value at that point, and we test to see if it is within the range of tolerance for our given problem. And if it's not, then we're going to repeat the same thing we just did. We're going to take the linear approximation, the tangent line, and we're going to find the root of that. It's going to be over here, and that'll be x2. And so you'll plug it in, and you'll do the same process starting at x1. And if you continue this forever, you can generalize this by saying that xi, we'll call whichever x we're using, we'll index it with I, will always be equal to the term that came before it, xi minus 1, minus the function value at xi minus 1, divided by the derivative of the function at xi minus 1. And we're going to just keep repeating that until f of xi becomes close enough to 0 that it's within our tolerance range. And so what that will look like is we're going to say that while the absolute value of f of xi is greater than 0, we're going to keep going through this process. We're going to calculate f of xi. We're going to calculate the derivative. And then we're going to proceed to find the next xi, and we'll update it. So you will set xi equal to xi minus and then you just repeat this process until this condition is met. The absolute value of your function at our value xi is within the tolerance. It's less than 0. And that's about all there is to it. It's just a pretty basic iteration that'll zero in on the 0 of the function quite quickly, actually, in most cases, assuming you have a sufficiently smooth function. Yeah, so that's all there is. And now just to explain this week's project a bit to you guys, what you're going to be doing is you're going to be comparing this method, Newton's method, to the method you saw last week, the bisection method. And more specifically, what you're going to be doing is comparing the the tolerance value that you're using to the amount of iterations necessary, and just creating a graph of that, comparing the iterations versus tolerance for the Newton's method, and then iterations versus tolerance for the bisection method. Yep, thank you very much. Hope that was helpful.